Okay, let us consider the case of spline interpolation technique. So in spline, before we go to spline interpolation technique, we just discuss what are the importance of the linear interpolation and polynomial interpolation techniques. So in case of linear interpolation, what we do is that if you are having two data points, if you are having two data points like this, so we will find out what are the missing data points in between these 2 points. So we use two nearest data points for interpolation in order to find the missing data in between these two data points available. And it is very simple, but it is not that much accurate. For example, if you are having some data points like this, and if you want to interpolate by using linear interpolation technique, then it will be like this. So you can see that it is not that much accurate, or which is not that much smooth, right? So what you can see is you can see that the interpolation or the data, it may not be exactly the same as what you can see from this interpolation, linear interpolation. So it is not that much accurate, or in other words, we can say it is not that much smooth. So if you consider again the smoothness of this, we were expected to have a line for this kind of points. We are expecting something like this. Okay, so it should be some smooth curve instead of a linear curve. Okay, so we can draw it again on like this. It should be like this, something. It should be much more smooth curve than the linear curve. So in such cases, okay, like this. So in such cases we can see the linear interpolation technique is not that much smooth. So it is not that much smooth. And the third one is that it is having some discontinuous slope. For example, if you consider the nearest points, for example this point, we have a slope which is positive, and at very near to that, the slope is negative next to the node. So near to that node region or the node points, we have two different discontinuous. So we have different slopes near to these data points. So that is another disadvantage. We have discontinuous slope near to this node region. And third one is that we can say it is not infinitely differentiable. What I mean by that is if you are having all these data points, but if you are considering these points at the nodes, or the points that is what we call as nodes, that is the data points. Okay, so these data points or the nodes will not have any difference. It is not differentiable at that points. So the function is not differentiable at these points. Okay, so this is another disadvantage. In other words, if you are considering the polynomial interpolation, so if you are using an nth degree polynomial for interpolation with complete data points available, so what we mean by this this polynomial interpolation is that if you are having some kind of data like this, as previous figure, so if you consider any n degree polynomial, then it will fit like this. Okay, so it will be fitting like this. So it is very smooth, and it will be much more accurate than the linear interpolation technique. But the problem with this polynomial interpolation is that it is computationally very complicated, because it has to consider an nth degree polynomial, and it has to find out what is the exactly fitting polynomial to these data points, and it is also having some oscillatory artifacts, especially at the endpoints. I can show you some other figure in here. So you can see from here, this is the blue color is shown, the curve with blue color is the original data, original curve. Okay, so this curve is our this one is original curve, but original function. But when you are considering the polynomial that is in red color, this one is polynomial. So if you consider the polynomial, it is having some kind of fitting, okay, some kind of fitting in this region, they are exactly balancing or coinciding these data points and the fit polynomial function. But when you consider these endpoints, they are having very large difference from the original function. So this is what we call as the oscillatory artifacts. So we can further go. For example, this is the for 11 points, for 11 data points we can count. This number of data points in this figure is 11. But if you are considering the same in this case, if you are using polynomial means with eq space nodes, which means that each nodes having the same space, like 0, 5, 10, 15, like that. So the space is same. So in such cases in polynomial we can see if you are increasing the number of data points, okay, in this case we are considering 15 number of data points, so we can expect the oscillatory artifacts at the end points is then increasing. It is having more correlation, or what we say, that fitting at the center region. But when it goes far from the center portion or the middle portion of the curve, or at the end points, it is having some oscillatory behavior. So this is not good for our this interpolation technique, because at the end point we will be getting very oscillatory nature. So it is a drawback of the polynomial interpolation. So in polynomial interpolation, what we do, we will consider any polynomial, for example a0 plus a1x plus a2x cube plus a2x square plus a3x cube plus etc. So any kind of such polynomial we can consider with some order, n order, okay. If you are having nth order polynomial, then we use that polynomial to fit our data points which is available, and we will find out what are the missing points in between those data points. So that is the method what we use in the polynomial fitting. But the polynomial fitting, how it is different, the polynomial interpolation from the linear interpolation, is that in linear interpolation we use the adjacent or nearest data points, okay. But in a polynomial interpolation we use all the data points at a time in such a way that they should fit exactly in all these points. So it will be almost going through all the points that is available. So that is what is polynomial fitting. So the polynomial fitting having some computational complication and the oscillatory artifact at the end points, that is the drawbacks with the polynomial interpolation. So we can neglect these two drawbacks by using the spline interpolation. So by using spline interpolation we can remove these kind of limitation with linear interpolation and the polynomial interpolation, especially the polynomial interpolation. But polynomial interpolation is much more better than the linear interpolation, because you will get a very smooth curve, and you will also get the node region will get it will be differentiable as compared to the linear interpolation, because it is having some change in these points. It is differentiable, and it is also differentiable in all points. So it is infinitely differentiable. In other words, it is we can differentiate the this polynomial at any data points in this curve. So these are the advantages of the polynomial, but still it is having some oscillatory artifact at the end points, and it is also having some computational difficulties. So we cannot rely on polynomial interpolation when you're having a large number of datas. Okay, that's the difference. We will continue the remaining thing, spline interpolation, in the next video.